You know that feeling, right? Sitting by a crackling fire on a chilly evening, the warmth just washing over your face. Have you ever stopped and wondered, how exactly does that heat get from the fire to you? Well, today we're going to join two kids, Pema and her brother Paulden, who are doing exactly that. And together we're going to uncover the invisible forces that move heat all around us.
This is the big question they were kicking around. See, Paulden had just been to Kerala, where it's all warm and humid, which felt like a totally different planet compared to their cold home in Gangtok. It's such a simple question, but the answer is pretty incredible.
All right, let's dive right in. The thing is, heat doesn't just have one way of getting around. Nope, there are actually three totally different ways it travels. And we're going to explore every single one just by using what Pema and Paulden noticed during their evening by the fire. So as they're enjoying the fire, Pema notices her grandmother cooking dinner in this big metal pan. And that simple observation, well, that's our gateway to understanding the very first type of heat transfer. Paulden's got a hunch it's because metals are good conductors of heat. But what does that really mean? How does heat actually move physically through a solid object like a pan? Okay, let's check out a classic experiment that really makes this whole thing visible. Picture a metal strip. We've stuck 4 pins to it using wax, all in a row. Now we heat just one end of that strip with a candle. What do you think is going to happen? Do they all fall at once?
And there you have it. The first pin drops, then the second, then the third. It's a perfect little sequence. Now this isn't random at all. It's a huge clue. It's telling us that the heat is literally marching down the strip from the hot end to the cold end.
And this is our first process, conduction. The best way to think about it is like a chain reaction. The tiny particles at the hot end get super energized, start vibrating like crazy, and bump into their neighbors, passing that energy along. But here's the key thing. The particles themselves don't go anywhere. They just pass the heat energy down the line.
Now, not all materials are created equal here. Metals like steel, they're fantastic conductors. Their particles are all packed together in a way that makes passing energy super efficient. But other things like wood or air or clay, their particles are arranged differently, so they're really bad conductors. We call those insulators. And that is exactly why the handle on a metal cooking pan is usually made of wood or plastic. It slows the heat right down.
And this idea isn't just for cooking. It's used in building too. In the Himalayas, a lot of houses are built with walls made of wood and mud. Why? Well, because those are great insulators. They trap the heat from the fire inside the house, keeping it cozy even when it's freezing outside. Super clever, right? Just basic physics at work. All right, let's head back to the fireplace. Pema's sharp eyes spots something else. The smoke from the fire, it isn't just spreading out everywhere. It's moving in a very, very specific direction.
Yeah, why does it always go up? It never just hovers or sinks or goes sideways. This simple little observation is about to open the door to our second method of heat transfer.
Check out this other neat experiment. You take 2 paper cups and balance them on a stick, like a little seesaw. Then you put a burning candle under just one of them. And what happens? The heated cup starts to rise. The whole thing tilts. So what is going on with the air inside that cup? This, my friends, is convection. It happens in fluids, so that means liquids and gases. When you heat a fluid, it expands, becomes less dense, and basically it gets lighter, so the hot, right stuff rises. Then the cooler, denser fluid sinks down to take its place, gets heated up, and then it rises too. You get this constant circular flow, a current. That's what's happening to the smoke, and that's why our paper cup went up. And this isn't just some small thing happening over a candle. Oh no, this happens on a massive scale. Think about the beach. During the day, the land heats up way faster than the sea. All that hot air over the land rises, and the cooler air from the sea rushes in to fill the gap. We call that a sea breeze. Then at night, the whole process flips. It's all just one giant convection current. Okay, so we've got conduction for solids and convection for fluids like air and water. But there's a problem. Pema and Paulden aren't touching the fire, so it can't be conduction. And we know the hot air is rising away from them, so it's not convection. So how in the world are they still feeling that warmth on their faces? This is the last piece of our puzzle. There has to be a third way for heat to travel. One that doesn't need particles to bump into each other and doesn't need fluids to flow around. And that third way is radiation. Heat can also travel as invisible waves, just like light waves. And here's the absolute mind-blowing part. It doesn't need a medium to travel through. It can travel through the total emptiness of space.
This is it. This is how the sun's heat crosses 93 million miles of nothing to reach us here on Earth.
And we actually use the principles of radiation every single day. Think about it. In the summer, why do we wear light-colored clothes? Because they reflect most of the sun's radiant heat, which helps keep us cool. And in the winter, we wear dark-colored clothes because they absorb more of that radiant heat, which helps keep us warm. It's that simple.
So, there we have it, our 3 methods of heat transfer. But the real magic is that in the world around us, these things rarely happen all by themselves. Most of the time, they're all working together.
So let's see how this all works together. Just think about heating a simple pot of water on the stove. The flame heats the bottom of the pan through conduction. Inside, the water starts to circulate. Hot water rises, cold water sinks. That's convection. And if you put your hand near the side of the pan, you can feel the warmth without touching it. That, of course, is radiation. See? All 3 working in perfect harmony in one simple system.
And if we zoom out, these same 3 forces are responsible for enormous things. The sun's radiation heats the oceans, causing water to evaporate. Convection currents in the atmosphere move all that water vapor around, forming clouds. It's like a gigantic heat engine that powers our entire planet's climate.
So, from the cozy warmth of a little fire to the giant global water cycle, the movement of heat is absolutely everywhere. It's in how we dress, how we build our homes, how our entire planet works. The next time you feel the sun on your skin or hold a warm mug of coffee, just take a second to think about those incredible invisible forces: conduction, convection, and radiation.